All right, so take a few seconds, open up to that packet that I gave you for the quote-unquote warm-ups, and let's look at number 4. We want to know if it says show that a function is even, how are we going to do that? Well, if you should remember, an even function is a function that is symmetrical about the y-axis, like, for example, y equals x squared. And basically that happens every time when you plug in an even number into the function, you get the same as if you plug in the opposite. I'm sorry, I meant positive versus the opposite. So the way that we do this is we show that f of x is equal to f of negative x by plugging negative x into the function f of x and simplifying. I can show you here that f of negative x will be negative x squared, which is the same thing as x squared. So in this case, f of negative x equals f of x. All right, showing that a function is odd. A function is odd if it is symmetrical about the origin, like y equals x cubed. And if you remember how to do that, if we plug in a positive number like 1, we should get the complete opposite result if we plug in a number like negative 1. So the way we do that is by showing that f of negative x is equal to the opposite of f of x by plugging negative x into the function and simplifying. Yet again, let me show you what that looks like. So if we evaluate f of negative x here, we get negative x cubed, which is negative x cubed, which is the opposite of f of x. All right, last but not least, if I want to find the interval where a function is increasing. When you see the word increasing and you're talking about a function increasing, you should think about f prime of x. And we're going to use f prime of x by finding f prime of x. We're going to set it equal to 0. We're going to solve for x. We're going to put those values, x values, on a number line. And we're going to plug the numbers into the derivative to check where it's positive. Where the derivative is positive is where the function is increasing. All right. So today is Tuesday, March 15th, and we're still working on 7.1, which is integration or integrals as a net change. And your homework tonight is page 386 from numbers 12 to 20 all. All right, so example number 1. We didn't really get a chance to do too many examples yesterday, so let's kind of work on it a little bit more. I want to find the net area under the curve. And net area is just like displacement that we had talked about yesterday. And to find the net area, all we have to do is integrate. And so if we are integrating from 0 to 4, x squared minus 4 dx, we will get the integral of x squared, which is x cubed over 3, minus 4x. We're doing this from 0 to 4. Which will, if we plug in 4 cubed, 4 times 4 times 4 is 64 over 3, minus plug in another 4. This is 16. Plug in my 0. I'm going to get 0 for both of them. So 64 over 3 minus 16. If I want to combine those two terms, I have to give them a common denominator. So I have to times this by 3, 16 times 3, which is 48. And 64 minus 48 is 64 minus 48, 16 over 3. So this is the net area under the curve. Now what we mean by net area is taking negative numbers and keeping them negative, positive numbers keeping them positive, and that means the negative actually subtracts away from the positive. All right, so the next question, example number 2, is find the total area under the curve. When I say total area, what I mean for this is I want to know exactly how much room is between the curve and the x-axis, and I want to make all of the room positive. I don't really care that it's below or above the x-axis. So find the total area under the curve on the interval from 0 to 4. If I am looking at the curve, it's x squared minus 4, so you should know the y-intercept is 4. X squared is a parabola. I can find out when it crosses the x-axis by setting x squared minus 4 equal to 0, finding those zeros. So x squared equals 4, x equals plus or minus 2. So this point right here is 2. So if we want to find the total area under the curve, I want to know the area from 0 to 2. And I'm starting at 0 because that's the beginning of my interval, not just for any other reason. I'm going to do the interval from 0 to 2 of x squared minus 4x dx. And I would anticipate that number to be negative based on the fact that graphically it's below the x-axis. So let me come back. I'm going to look at my answer. It was x cubed over 3 minus 4x from 0 to 2. And if I plug in 2, I've got 2 cubed, or 8/3, minus 8, which will be, let's just look at that. If I give this denominator of 3, and I multiply the top by 3, that's 8 minus 23, which is going to be 16/3. But it is negative because it's below the x-axis. Okay. If I get the other area, let's go back up here. And now let me still evaluate this. But now I'm going to go from 2 to 4, which goes to the end of my interval. X squared minus 4. It's not 4x. It's actually x squared minus 4 dx. Let's integrate that. Still, it's the same thing. X cubed over 3 minus 4x. I'm going from 2 to 4. I know when I plug in 4, I get what I had above, which was 4 cubed, which is 64 over 3 minus 4 times 4, which is 16, minus, and now I'm going to subtract what I get when I plug in 2, which is the 8/3 minus the 8. So what this is going to find me is the area that's above that curve right there. So 64 over 3, let me make this over 3, times it by 3, and 16 times 3 is 48, and 64 minus 48 was 16/3, minus, and I just saw what happened over here, 8/3 minus 8 we said was negative 16/3, so we actually end up getting back 32/3. So that's the area above the curve. So for my total area, and feel free at any point in time if you need to pause this, rewind, that's totally fine. My total area, not the net area, but the total area, is going to be 16/3 from below the x-axis plus another 32/3 from above the x-axis, which turns into 48/3 total. And that's kind of the topic that we're going to be exploring. Okay, let me just do a couple more examples that will pertain more towards your homework. All right, looking at the top here. We talked about yesterday how if you integrate a rate, you get an amount. So basically, if we're looking here, we've got modeling the effects of acceleration. A car is moving with an initial velocity of 5 miles per hour at the rate of acceleration is equal to 2.4 t miles per hour per second for 8 seconds. And we want to know how fast is the car going when the 8 seconds are up. So if we integrate a rate, we get an amount. So if we integrate a of t, we will get v of t. So we want to integrate a of t from 0 to 8. A of t, which is 2.4 t dt. And if I integrate 2.4 t, I get 2.4 t squared divided by 2 from 0 to 8. 2.4 divided by 2 is 1.2. I'm going to plug in the 8 and square it. 1.2 times 8 squared, which is 76.8 miles per hour. And that would be the answer for A. All right, how far did the car travel during those 8 seconds? So, just like we had the integral of A of t equals B of t, if I integrate for, let's say, let's change this color. If I integrate v of t, I'm going to get s of t, an amount. And in terms of this would be distance. So if I integrate my 76.8 miles per hour, in fact, hold on one second. Let me come back for that. I'm being a little bit ridiculous. Not my 76.8 miles per hour. That was a specific number that came from 0 to 8. Okay, if I integrate my v of t, well, let's think about what my v of t is. My v of t came from the integral of a of t, and my v of t based on this is 1.2 t squared plus my initial velocity, or plus basically some value c. That's my v of t. And we know that the initial velocity is 5 miles per hour, which means when t equals 0, v was 5. So if I plug those numbers in down here, v would be 5 when t equals 0. This is 1.2 times 0 squared plus c. That tells me that c is 5. So if I integrate velocity, which will be 1.2 t squared plus 5 dt, I'm going to get position. Now I want to do this still for those 8 seconds, because it's how far did you go or travel during those 8 seconds. Okay, so I'm going to integrate this again. Integral of 1.2 t squared is going to be 1.2 t cubed over 3 plus 5t from 0 to 8. So this is the same thing as 0.4 times 8 cubed plus 5 times 8 minus 0 when I plug 0 into both terms. So 8 cubed times 0.4 is 204.8 plus 5 times 8, which is 40, which makes 240.8. All right, last example. Okay, so this doesn't only pertain to speed. Clearly, there's lots more examples of rates in the world. And so this is the rate at which a potato consumption in a particular country was C of t equals 2.2, 1.1 to the t, millions of bushels per year, with t being years since the beginning of 1970. And we want to know how many bushels were consumed from the beginning of 1972 to the end of 1973. So let's look at this. The general formula is that if you integrate a rate, you get an amount. So if I integrate this C of t, I'm going to get how many potatoes were consumed. Part of the trick here is finding out what your bound should be. So this is the number of bushels from the beginning of 1970. So from 1970 to 1971 would be 1 year. That would be from like 0 to 1. So from 71 to 72 would be from 1 to 2. So starting at the beginning of 1972, that's going to be 2. And to the end of 1973, that's 2 whole years. So that's going to go from 2 to 4. Now, since this is something that I'm not exactly sure how to integrate, or at least you guys don't have a rule for right now, 2.2 plus 1.1 to the t dt, we haven't done anything like that, I'm going to suggest you use your calculator for this one. And your calculator, if you remember how to integrate on your calculator, it's Math 9, which is FNINT. We're going to type in our equation, 2.2 plus 1.1 caret x, because that's our variable, comma x, the variable, comma 2, comma 4. That's your lower bound and your upper bound. So 2.2 plus 1.1 caret x, comma x, comma 2, comma 4. And that gives me 7.066. We always want 3 decimals. And that's 7.0663 millions of bushels. in those 4 years. All right, guys, just work on the worksheet for the rest of the class, and good luck on your homework. Thank you. Bye-bye.